Hello, everyone. We're extremely excited to present to you our final take on our design. Considering how unorthodox our situation is as students and yours is as administration, we're all stepping into uncharted territory here. So, thank you for taking the time to listen, and hopefully, we've all learned a little bit more about the many interesting shapes engineering can take by the end of it all. So, today we're going to talk to you about our research and practice in sloshing mitigation in three-dimensional rectangular tanks. First, I'd like to introduce our group members. The computational analysis was completed by Eric Novoselsky and Zach Hiller, who will talk to you soon about our software analysis and application. Our experimental analysis was completed by Pat Jennings and me, Matt Wilson. We're going to get into the physical prototyping, standards, specs, and impact analysis. All research and experimentation was done under the guidance of Dr. Farouk. I'd like to start with describing sloshing in general terms. Basically, you have a container filled with an observable fluid. The tank itself is not completely full. This creates an air-liquid interface where there is free volume for liquid to move around. The tank is then subjected to external forces. These forces can be caused by whatever mode of transportation it is that's carrying that tank, for example, locomotives or automobiles. These forces are characterized by any stopping, accelerating, or turning, which can cause heavy masses of fluid to move around uncontrollably inside the tank. This can present great risks to environmental and worker safety. These issues will be expressed more thoroughly in the impact analysis later on. So far, prior research and experimentation has been done from the standpoints of vibrational and oceanic engineering with applications in oil and gas, automobiles, and aerospace. A lot of that analysis has been based off of the implementation of solids within a fluid-filled tank. Our problem statement is defined by the design, building, and observation of a fluid carrying container with internal structures, based off of the research I've just previously mentioned. These solids will be implemented and aimed to reduce sloshing and its potentially harmful effects. As a means of promoting efficiency of spending, physical work, and experimental safety, detailed simulations using computer software will be used to support physical testing. Overall, this will reduce the need to buy excessive amounts of materials or work with unwieldy equipment or hazardous liquids. Our stakeholders include any major mass oil transporting companies such as PBF, Exxon, or AF Claveness. What is meant to be offered to them at this point is a safer form of transportation for drivers as well as the commercial promotion of better product safety. Other stakeholders include private researchers such as Dr. Farouk, who wish to implement safe, efficient testing and simulation practices for the sake of educational and applied learning practices. As for our approach, I had previously mentioned the split in responsibilities. These next few slides will detail some of the duties on each side. So, in the experimental work, we designed a setup consisting of a small-scale, clear-walled fish tank containing water with an optional baffle system and an electroresistivity probe. The tank itself was placed on top of a linear motion shaker table to produce sloshing behavior. Video recordings of individual runs were taken using an iPhone camera in order to document physical attributes of sloshing within the tank. Two standout prototypes were designed within the experimental portion of this project. The first being a new shaker rig that allowed for testing of various amplitudes and frequencies. This would be a cheaper option than a shaker table. The second being the electroresistivity probe, which would allow for dominant fluid analysis and comparisons to software data. In the computational work, the experimental tank was regenerated using LS-DYNA software. This software allowed for potential physical runs to be simulated using variations in tank shape, fluid type, frequency, and amplitude. Data retrieved for point-specific analysis of dominant fluid in the air-liquid interface could be easily compared to that found in the experimental work. More thorough computational analysis will be detailed later by Eric and Zach. Now on to Pat with the specs, standards, and designs.
Specifications and standards for both our experimental setup and our tank design with baffle are as follows. The amplitude variation, which was a new specification that was added, which states that we need to have an amplitude ranging from a ½ inch to 2 inches. This allows for better studying of how the tank moves and how the water flows up and down based on our frequency. The rest of the specifications are small scale, frequency, lightweight, and visibility. These all play crucial roles into studying how the water moves when sloshing. Standards for our project come from two main groups, the ASME boiler and pressure vessel code and also the FMCSA regulations and standards from Section 393. The ASME Boiler and Pressure Vessel Code covers any tanks that are enclosed, especially when carrying highly flammable liquids such as gasoline, whereas the FMCSA regulations from Section 393.65, .67, and then .100 to 136 cover aspects of fuel systems, liquid tanks, and securing standards to each vessel. Since the pandemic of COVID-19 has hit the United States, we had a few changes in the scope of our project based on such. One, the prototype development. We were stuck with only one working prototype, and our second prototype, that was in development, was unfortunately stopped because there was limitations and some of our supplies was stuck in the Drexel laboratory, which we cannot retrieve. Secondly, all of our calculations and modeling have gone from 50% experimental and 50% computational to purely computational at 100%. Due to the pandemic, our second improved shaker rig was stuck in the design and construction phase. As you can see from the drawing on the right, that is an accurate drawing of the parts drawn to scale for the improved shaker rig that would be constructed with the drawing on the left. The new shaker table allows for a higher weight of the tank, which allows more water and more experimental testing, along with a lever arm pulley system, which allows for an adjustable amplitude. These, together with a half power horsepower motor, allows for different speeds because of the variable speed motor. For our design, our two designs of two different prototypes. Again, the drawing on the right being the new improved shaker table that was never constructed, unfortunately. But our prototype 1, which you'll see later in the presentation, is fully functional and allows for some experimental results. The new prototype with the wood base and the wheels allow for heavier tank usage and more accurate experimental testing. Our functioning prototype 1 is pictured here. This, using the pre-constructed linear shaker table, allows us to take experimental data and compare it to our simulations. Unfortunately, this prototype has a fixed amplitude of 0.5 inches, which really limits us to testing. Also, the shaker table has a weight limit, which does not allow us to fill the tank over half full. These limiting factors were which drove us to create prototype 2. Now, from that, you can see I have a prototype demonstration right here. So we can sit here and watch this really quick and see what some of our experimental results look like. As you can see, the shaker table, though it is moving not a great deal, is moving fast enough to create sloshing inside of the tank. That was a test at high RPM, and as you can see, the tank is moving very quickly, which creates the ripples in the center of the tank.
Here is a design sketch of the circuitry layout for the ER probe. The probe itself is designed to be able to be placed at any point within the tank, either suspended in the air or held in the water. With the resistivity data, it is possible to create a plot of the dominant fluid against the runtime of each sloshing trial. These plots can be compared to software-generated plots to compare data and eventually create a working baffle system within the tank. Some key components of the probe include a voltmeter for data acquisition, a battery and resistor for electrical current control, and a probe electrode and reference plate configuration for point analysis and circuitry completion.
Design methods for our project were fairly simple. We used soldering to connect each different aspect of the probe and its circuitry together. For the new and improved shaker rig, we used a circular saw and power tools to combine each aspect of itself, including the base to the wheels, the lever arm and pulley, and the motor to the base. For the materials that we selected, we used wood and stainless steel. These offer a high strength and high weight carrying capacity, which allows us to fill the tank almost completely full and test for different scenarios.
LS-DYNA is a simulation software package that can be used to model and test various types of physical systems. While LS-DYNA is generally used for solid interactions, liquids can be studied using the software by creating a solid and giving it properties of a liquid. Using LS-DYNA, a small-scale rectangular tank was modeled and used to simulate the liquid reaction under various motions. The plan with LS-DYNA was to model a rectangular tank, add baffles, and run simulations to compare the effectiveness of various baffles. However, a lack of experience with the software prevented us from achieving this. Since LS-DYNA is primarily focused on solids, there are not many examples involving liquids to pull from, and our lack of experience led to issues that we could not fix. The top example is a simulation that studies the ricochet of a projectile at an air-water interface, which was provided by Hussein Basandawa, a PhD student studying under Dr. Farouk. The bottom example is a rectangular tank under linear motion, partially filled with water.
The wide-ranging impacts are detailed here. In terms of environmental effect, this project and design method will promote less damage to the ecosystem. This translates to less emissions and brake wear in transporting vehicles, as well as in extreme cases, less hazards like leaks, rollovers, explosions, fires, etc. It'll also produce less waste of natural resources, such as crude oil, potentially lost through those hazards. In terms of ethical effects, public health and safety are held paramount in this design. Environmental risks translate clearly to ethical risks to surrounding human populations like respiratory damage from those airborne toxins. With better control of freely moving substances, drivers would be at a reduced risk while transporting materials. With a design dependent on software application, harm in testing with heavy uncontrollable materials is greatly reduced as well. In terms of societal effects, better safety practices present a common ground for environmentalists and industrialists, which means less walkouts and protests for unsafe conditions. In terms of economic effects, for industrial upstream aspects, some negatives include upfront costs for extra materials, more detailed design parameters, and implementations for tanks. Some positives include once those types of designs become industrial norms, overall cost becomes negligible, knowledge becomes standard and widespread throughout the industry. For consumer downstream aspects, a clear negative is higher cost for more detailed designs and final products. Some positive aspects are the reduction in hazards, which means saving resources and therefore saving money. People will pay to feel safe, so any money paid for safety can be seen as a fair price.
To further understand sloshing, we gathered data from all of our simulations. This data was then analyzed by picking a single element from the mesh. The element, as seen by the highlighted blue square, sits on the surface of the liquid at rest and is stationary relative to the tank. For all the following slides, all the data was taken for this specific element. One way we analyzed our system was to plot dominant fluid material at the element over the duration of the simulation. These two graphs are for water and gasoline with a motion of 1 millimeter in amplitude and 0.07 hertz in frequency. Dominant fluid material basically describes which fluid, whether it be water, gasoline, or air, is the dominant one at a specific time. Since our system had two main fluids, the values for the graph can either be 1 or 2. A value of 1 describes air, and a value of 2 describes water or gasoline. As shown by these two graphs, at low amplitude and frequency, water and gasoline act nearly identical. They both exhibit little movement because the dominant fluid doesn't change until over halfway through the simulation, and it only changes about 3 times in 500 milliseconds. Now, when amplitude and frequency increase, there are differences. In these graphs, the amplitude is increased to 5 millimeters and frequency to 0.15 hertz. The changes in dominant fluid now have sharp spikes over the duration of the simulation. These spikes indicate rapid change between the fluids. For the same motion, gas has less change in dominant fluid over time. Another way we analyzed our system was to look at volume fraction. Each element has a volume, and in that volume, there can be either one fluid or a combination of both fluids in the volume. Volume fraction is plotted as a percentage, with a max value of 1. So 0 value indicates that the volume is comprised of 0 air, or all liquid, and value of 1 means the volume is all air. Again, at low amplitude and frequency, water and gas act extremely similar. Volume fraction is a convenient way to get a more in-depth look at the motion. It shows how there is still movement and volume change over the course of the motion that dominant fluid flow doesn't particularly show. When the amplitude and frequency are increased, again, water and gas begin to differ. The spikes on the water graph show a concentrated motion all occurring between 200 and 375 milliseconds, while gasoline changes are more spread out over the entire simulation, starting around 225 milliseconds to the end of the simulation. And there are some similarities and differences, of course. The main similarity between water and gasoline was that at low frequencies and amplitudes, they acted pretty much the same, nearly identical. However, there were differences at higher amplitude and frequency. These differences boil down to gasoline having a more spread out motion with slightly more changes or spikes in volume than water, while water has its peaks extremely close together and concentrated.
The experimental portion of the project, which was focused on creating an experimental apparatus that could be used to study sloshing, was successful. One of our stakeholder needs was a working prototype that can be used in the future to continue studying sloshing, along with the prototype being adjustable and improvable for future studies. This goal was accomplished with our first prototype and was being expanded upon with our second until COVID-19 put a halt to our experimentation. Our original prototype, pictured here, was able to subject a rectangular tank to linear oscillatory motion and simulate sloshing on a small scale. The second prototype, which remains unfinished, was to expand on this by allowing amplitude to be adjusted, which was not possible with the original. If experimentation had not been stopped, the second prototype would have been completed and experimental studies on sloshing with baffles would have been performed to gather data on the effectiveness of different baffles on minimizing sloshing. While we were not able to gather data on different baffle configurations, the working prototype and designs for the second prototype met one of the key stakeholder needs for the project. On the computational side of the project, the results were not as positive. LS-DYNA was used to create small-scale tank models which were partially filled with water or gasoline that were simulated under various linear motions. Even though results with these models were obtained and some differences between gasoline and water were discussed, we were not able to gather results for tanks with baffle systems implemented, which was a major goal going into the project. None of us had prior experience with LS-DYNA, so we had hoped to learn the software quickly so it could be used for results, but this was not the case. LS-DYNA proved very difficult to learn, with very specific settings needed in order to have successful simulations, along with vague error messages. Since none of us had experience in a similar software either, even creating the models was a difficult task. We were provided with a tank model that included a vertical baffle, but there were errors present when we assigned keywords that we were unable to work out. Along with difficulties in learning the software, simulations took a very long time to run, taking 2 to 3 hours to run a simulation for 500 milliseconds. Without a designated computer to run these simulations, longer time intervals were not possible, especially during the spring term when all classes were moved online. Even though we were unable to gather results on various baffle systems for our tank, the files and simulations we were able to produce would provide a good starting point for anyone trying to continue our work in the future. With some more troubleshooting, the model with the baffle could be fixed and the results we had hoped to achieve could be obtained much quicker than if the process was started from the beginning. Overall, senior design has been a challenging but useful experience, teaching us how difficult it can be to work on a long-term project with the same group. We learned how much of a struggle it can be to stay in communication with everyone involved, work around conflicting schedules, and balance our time between senior design and other endeavors. Finding this balance between senior design, other classes, a full-time job search, and our personal lives proved to be the most difficult obstacle to overcome. The most enjoyable aspect of the project was working with people we have known and been friends with for years. This made it easier to communicate with each other and hold people accountable for their work since everyone was comfortable with each other. Some major challenges we faced aside from finding the required balance of our time include struggles learning LS-DYNA, a major part of our project that we had no prior experience with, and adapting to the changing environment with the COVID-19 pandemic. Due to the pandemic, communication was much more difficult and all experimental work was halted. This definitely hindered our outputs as we planned to gather experimental data during the spring term, which was not possible. Along with challenges associated specifically with senior design, the pandemic also made it more difficult to stay motivated with having to adjust to a whole new learning environment just a few weeks before we were set to graduate. As a whole, senior design was a beneficial experience that was ultimately hindered by the unexpected and unavoidable events associated with COVID-19. During the course of our project, we learned many lessons. There were two major lessons that we learned, one from the experimental side of the project and one from the computational side. In the experimental area, the major lesson we learned was that the easiest and quickest option may not always be the best option. For our first prototype, a linear shaker table was purchased and was used to induce motion to a small-scale tank. While this option worked and our prototype was a success, the amplitude associated with this shaker table could not be adjusted, and our second prototype, a shaker rig we began to assemble ourselves, was started. We were unable to finish this prototype, but it would have had the same benefits of the shaker table along with the ability to adjust amplitude, and this would have been less expensive than the shaker table. If we had gone with this more time-consuming prototype in the first place, we would have saved money and had more customization options. On the computational side, the major lesson learned was to understand the software we were planning to use before we decided to use it. LS-DYNA was suggested as a software that could be used to simulate the effects of sloshing, which it was, but we did not have experience in this software, and this is where a majority of our problems arose. We were overconfident in our ability to learn the software quickly, and when it proved more difficult than we expected, we did not have many options. In hindsight, we should have done more research on LS-DYNA and attempted to learn the software before agreeing to use it, as well as research other software options that could have been used for similar purposes. While this oversight on our end hindered our attempts to gather data and produce simulated results, the lesson learned here is very important and will benefit us in our future endeavors. If our project were to be continued by us or another group down the line, the immediate future would entail finishing the second prototype and conducting experiments with the prototypes implementing different baffles into the system. Along with this, LS-DYNA troubleshooting would continue so simulations with various baffles could be run. Further in the future, the existing prototypes could be continuously upgraded, either by obtaining better equipment or adding things to further improve the effectiveness of the experimental apparatus. While our prototypes focused on rectangular tanks, adding equipment that would allow for cylindrical tanks or irregularly shaped tanks to be studied would greatly add to the potential of our prototype as a tool to study sloshing. Recommendations we would give to students who are beginning their senior design experience include researching the area that they are focusing on. Researching what others have done for a particular topic could lead to ideas or design concepts that could be used and adjusted for their projects. Also, we would recommend to start working early and get as much done as quickly as possible. Students entering senior design should avoid putting things off until later terms in case something happens and what was planned could not be finished. Lastly, we would recommend that the students working in senior design get comfortable with the tools they plan on using before they decide to use them. If they are unfamiliar with a tool or program, they should put the time in to get an understanding of the tool as well as look for other alternatives that could prove more useful or easier to pick up.
And for project management, there's communication, organization, and tools are some of the key components for a project to have success. Our group used meetings, messages, and even Zoom to communicate. We use Google Drive and meeting minutes to stay organized, and we use tools such as LS-DYNA and a shaker table to complete our project. The table to the right shows a detailed outline of the entire budget over the fall, winter, and spring terms. The total end cost for our entire project was $971.91. The image you see on your screen shows our Gantt chart over the entirety of senior design. Fall and winter terms stayed pretty much on track for the most part, as you can tell by the just purple bars. But starting with the experimental setup, we started to experience some problems, and it trickled down all the way, obviously, to the end.
Here is a list of our references. And here's a list of some of our contact information if you have any questions later on during the process.